All right. Thanks everyone for attendance, and it has been a very long time when we invited the speakers, but this time I think we are very glad to invite Jun, and he is a PhD student under Prof. Liang Zhengkai. And I think you have already checked Jun's profiles, and as a fourth year PhD student, he has published quite well in the field of security. He has NDSS, ISTA, Using Security, and Auckland, so very strong publications. And also his research interest is in the interaction of system security and recommendation systems. And just based on the talk, you know that his research focus is on intrusion detections, and which might be our future directions. So basically intrusion detections is quite relevant to our Cisco and potential NCS work. So now I will give the stage to Jun, and I think it's a good opportunity for us to learn more about their intrusion detection and the log analytics work, and also maybe we can have extensive further discussions. Okay, Jun, please.
Okay, thanks for the introduction. Let me share my screen. Okay, can you see my screen?
Yes, it's visible.
Yeah. So you can see that.
Yeah, perfect. Let's get started. Okay, so good morning, everyone. I'm Jun from Zengkai's group, and today I will introduce our recent work, SHADEWATCHER, recommendation guided cyber threat analysis using system audio records. Nowadays, we have been witnessing a large replication of cyber threats that intentionally target large organizations. For example, Microsoft, Cisco, and Twitter. While performing cyber attacks, attackers inevitably leave traces of footprints in the victim systems. A common question that faced by security analysts is how to combat cyber threats through these footprints. Audio records are a common footprint, which proves to be a valuable data source for analyzing cyber threats. They can provide a low-level view into cyber threats by monitoring system entity interactions. For example, when an attacker infiltrates the sensitive file, the password file here, his footprints will be recorded as system calls in the audio logs. To facilitate attack detection and investigation, audio records are typically navigated through a provenance graph that describes the system's historical contents. Here, by following the data provenance, we can find that the password file is leaked to a remote server through malicious executables. In general, system auditing can connect separate attack steps, presenting the overall attack scenarios for security analysts to analyze attackers' footprints. Based on how audio records are used in cyber threat analysis, existing approaches can be roughly categorized into three directions. Statistics-based approaches quantify audio records' degrees of suspicion by their historical frequency. However, the primary concern faced by this line of research is the number of false positives generated by rare but benign system activities. Specification-based approaches can maintain a low false positive rate by matching audio records against the knowledge base of security policies. Unfortunately, such policies are time-consuming and error-prone to develop because they heavily depend on expert knowledge. Learning-based approaches nowadays will train a model of benign behaviors in audio records and then detect deviations as cyber threats. However, existing data-driven or learning-based approaches only produce detection signals at a core screen level, specifically the behavior level, which requires extensive manual efforts to review individual audio records in behaviors to locate the particular system activities that triggers the detection signals. And in this work, we aim to address these limitations. Our solution is based on the observation that cyber threats can be revealed by determining how likely a system entity would interact with another entity. In particular, unlikely or unintended system entities are strong indicators of cyber threats. For example, sensitive files, like for example, the password files, normally do not interact with public networks, which otherwise indicate its data exfiltration behavior. The likelihood of such interactions can be estimated using historical system entity interactions. For example, if we observe that a process, the GT cache, has interact with the process status file, then it's reasonable for this process to interact with another process status file. This problem looks like a recommendation scenario, where the primary goal is to determine how likely a user would interact with an item. Earlier recommendation systems comprehend user preferences by finding similar users using historical user item interactions. To illustrate this idea, we use a movie recommendation scenario, where Alice is a target user for recommendations. And here, because both Alice and Bob have watched Iron Man, the recommendation systems would consider that these two users are similar. And because Thor is Bob's favorite movie, it will be also recommended to Alice, because Alice is similar to Bob. However, user item interactions are insufficient to recommend items disconnected in historical interactions. For example, the Avengers here. To address this issue, modern recommendation systems would adopt item citing information to form a high-order connectivity that links similar items. Here, since both Iron Man and the Avengers are action movies and produced by Marvel Studios, we can find the multi-hop paths that connect the Alice and the Avengers here based on Iron Man and the action, or Iron Man and the Marvel Studios. As a result, the Avengers would be recommended to Alice because it's connected to Alice and similar to Iron Man. The Little Woman here would not be recommended because it's not connected to Alice. Inspired by recommendation systems, we make an observation that similar system entities in audio records would share preferences on their interactive entities. For example, sensitive data do not like interacting with public networks. To better uncover system entity similarities, we aim to identify high-order connectivity based on citing information of system entities. For example, if two process status files were correlated through process status information, then we would determine that they are similar and share the probability of interacting with the other processes. For example, the GT cache process here. Therefore, we can formulate cyber threat analysis based on audio records as a recommendation task, which models how likely a system entity would interact or would prefer its interactive entities. To perform recommendations on audio records, we propose SHADEWATCHER. It takes audio records as input and then build a knowledge graph. Based on the knowledge graph, SHADEWATCHER trains a recommendation model to process detection signals that represent adversarial system entity interactions. We also provide the capability for SHADEWATCHER to update its recommendation model based on analyst feedback on detection signals. First, given audio records on a host, we pass them into a provenance graph, where the nodes in the graph are system entities. For example, a process, a file, and a network socket. The edges in the graph represent the system cores. Especially, we consider that two system entities are interacted if there exists a path that connects them in the provenance graph. We extract all the system entities for cyber threat analysis into a bipartite graph, where the nodes in the graph are also system entities, but edges represent system entity interactions. While system entities send information.
Sorry, Zeng. So for the interruption, so would it be more specific? Give an example of interaction. So I understand. So the system core, and here usually in the knowledge graph we have a subject and object, and for the system core, and how could so given a link, how could a password file can have a system core to the GT cache? So would it be more specific on that?
Okay, so first of all, the system cores will be recorded in the audio records. So you can consider each log entry in the audio records as a system core. So it will describe the relationships between two system entities. For example, here, for this system core, you can find that the GT cache read the password file. So this will be a system core.
So the system core is behavior and read and write, or?
Yes. So the system core can be read, write, open, close for file operations.
And how many? Yeah. For how many system cores do you have? Or there's a large number of system cores, or there's quite a limited number of?
Okay. So you mean the types of system cores? Okay.
Yes.
So if I remember correctly, the NUS operating systems support over 200 system cores. And in this work, we aim to analyze 32 of them, which are commonly used in our daily operations.
Yeah, how many program entities? I understand. So, yeah, how many types of program? Sorry, this is supposed to be the system entity, right? So a files, a servers, and how many types are there?
Okay, so each system entity here in the system would represent a process or a file or a network socket. Yeah, for example, this password file is a system entity, and it's a file, and this GT cache is also a system entity, and it's a process.
It's a process. Okay.
Yeah.
Yeah. So. And then maybe I asked this question too early. My next question is, so for log information, I understand log is almost a semi-structural text. So is that easy to? So it's quite easy to get the file name, like etc. password, and the PID, etc. And how do you process a process name? Is there the specific format, or there's a challenges using some NLP to extract the corresponding entity?
Yeah, that's a good question. So here we will collect the audio records using a tool called the Audit. And this Audit will produce the audio records in the JSON format. So what we need to do is to process the JSON format to convert the audio records into this provenance graph.
I see. So that tool can already transfer the text information into some structure information.
Yeah, but it's not that
accurate.
Although it's very straightforward, but it's not that easy to process audio records. So for example, if we just take the open system core as an example, so the open system core will only give you the file descriptor. So for example, the read system core. What we can know from the system core read is that here we have the process, for example, the GT cache process, and it reads contents from file descriptor 8. but we do not know what file descriptor 8 represents. So that we need to do backward tracking and find the meaning of this file descriptor in the previous open system course. So because as you can say, there is a dependency. If you want to know the files for read or write system calls, you have to check the previous open system calls. And the same for the network connections. Yeah.
I see. For now, the logs, so there's I would like to say that the log is just from one source, right? So you don't combine the logs from different systems, different devices. You're just looking to the cloud or the cloud log.
Yes. Yes. So yeah. So previous world or recent world has tries to combine or unify different levels of audio record of system logs. For example, here we focus on the system audio records, which you can consider these logs as a system course. But recent world has also combined these audio logs with application logs, which are developed by developers.
Okay. Okay, see. So maybe on these slides, my last question is about your bipartite graph. So, and how do we decide the part in this bipartite graph?
Oh yeah, I think there is a okay. I think the reason you are confused by this bipartite graph is because I missed some details here. So first of all, let's consider this. Let's first imagine how we can extract the system entity interactions. So what is the system entity interaction? So basically, if we find that two system entities that are interacted in a province graph, we will consider that, hey, we find the system entity interactions. For example, you can see from this graph, from this province graph, there exists a path from the password file to this network socket, right? It will go through this 1, 2, 3, 4. It will go through these 4 hop passes, right? So in this case, we can consider that, hey, we find the path that links two system entities. Yeah, we find the system entity interactions. But the thing is that typically the province graph will be huge. So it's not possible to enumerate the connections between every two systems.
Every pairs,
every pairs. So you cannot just say, hey, let's extract all the pairs of system entities and say whether they are connected in the province graph or not, because it's impossible. So the way we do the system entity interaction extraction is to first we will extract behaviors here. So how do we define the behavior? We consider we will first locate all the data objects in the province graph. And then we will use the forward tracking based on this data object. For example, this one, we will then perform the forward tracking based on this data object to say or to extract all the system entities connect to it. And we consider this subgraph as a behavior. And the reason we do that is because in this case, we can exclude all the disconnected system entities.
I see. So more like the connection detect, more like something like connection detection, right? So a link between an interaction link between two entities means that there's supposed to be a path on the graph to connect one entity to the other. Am I understanding correctly?
Yes, correct. And
do you want to take?
Yeah, that's okay. I'm not sure why. Yeah, sorry.
Okay, so yeah, so for this bipartite, so maybe we can wait here for more of your understanding, to understand more about why you need to this bipartite graph. I understand this is more linkage, and once you construct this bipartite graph, and there is the hop limit. So from the password files to the servers, it goes through 4 hops. So is there a limit or?
Yeah, there is no limit here. We try to extract all the system entity interactions here because we do not want to miss any malicious interactions. So for example, if we set up a limit to find the interactions, it will be a problem. The problem is that if I'm an attacker, I can easily invade this detection by just inserting numerous unrelated system activities, so
Yeah,
that
yeah,
you will miss the interactions.
yeah. My question, I raised my question because the system, the graph seems super huge. So if we would like to build it, the connection between every peers, on, I'm not sure how the runtime efforts to build such a bipolar graph.
Oh yeah, but it's doable. Even though the graph can be very huge, but the thing is that after we build the graph, after we extract the behaviors, you can say that the whole province graph will be decomposed into a lot of subgraphs. And based on these subgraphs, it's possible to extract all the system entity interactions.
I see. And how about, so there's very minor, just be curious. So given the provenance graph, how, do you observe some loop there, or does the loop matters?
Oh, you can say, for example, here you can find the loop, right? But but the thing is that each edge will be attributed with a timestamp. So even though you have the loop here, but it doesn't matter because we only want to track the causality. So no matter, so for example, for this process, if this process has send a packet to this network socket many times, for example, 100 times, we only count one once, because as long as they are connected, we say that there is a causality between these two system entities, and then they are interacted.
And since is there very interesting explaining you're saying about time steps, so which means that some of the events are temporal, right? So
Yes,
is the
correct.
temporal order matters? For example, the ZTMP send packets to the servers and the server send it back, and maybe the semantics are different if the server send the request to the node first and then get response back, and suppose the order switch, the semantics different based on your provenance graph.
Oh, this is this is a very good observation. Yeah, the temporal order matters here, because let me consider an example. For example, here for this GT cache, if this GT cache first writes this file and then read this file, we can say that there is no interaction between this file to this one, because this write happens first before this file read. So when we try to extract the system entity interactions, we will consider or take the temporal order into consideration. Otherwise, we will get a lot of false positives interactions.
Okay, so in summary, so the temporal orders or chronological orders matters for deciding the causality, right? So, and I'm sorry, so the causality is more used to describe the events, right? Instead of the entity. So it is very hard to say one entity is a reason of the other entity. After all, the entity is a server, it's a process, it's a file. And when we're talking about causality, it's about event. It's saying the weather is bad, so I don't going to play tennis. So there's two events. And how do you convert these entity information into the event information in terms of the causality description?
Oh, yeah. So here we consider that there exists a causality between two system entities, as long as we can find the information flow from, for example, from system entity A to system entity B. So you can consider that in provenance analysis or in this provenance graph, we only track the provenance or dependency at a coarse-grained causality, as long as the two system entities, as long as we can find a path between two system entities, we will consider that they are causally connected.
So the causality is more like the data causality or the flow, the data flow causality.
Yes, correct. The information flow, basically.
So since we're talking about since the data flow information or data flow analysis is corresponding to the control flow program analysis, the control flow analysis in the program analysis field. So in this event, you can track in the control causality, which means that one event happens because of the other event happens. So are you looking to this kind of the causality?
Oh, here currently we do not look into this control flow because in provenance analysis, we mainly focus on the data flow or information flow. I mean, the data transfers among these system entities.
Okay. So the blue edges here, the interactions, is more about the information flow.
Yes. So basically, you can consider this as a information flow tracking or taint analysis at a level of system entities instead of instructions.
Okay, I think the explanation is quite clear here. Is there any of us have the further questions to Jing? I think he is quite an expert here. I think it's a very good chance to raise a question to the author, the first author of the papers. Yeah. So usually when we report the paper, anyone would like to raise a question?
Yes. Just like small details.
Okay.
Yes. Here on bipartite graph, there is an edge between etc password and prospect stat. Is it following from the provenance graph? Because I just don't see the information flow from password to stat in the graph above.
Oh, yes. That's a very good observation. So here, we also consider this interaction because the edge here is not read. The edge here represents a load, and when we say load,
you mean loading yes. Something? Okay.
Yeah, it's loading something, so it's different. It's different from read. We can see that the password file can somehow still manage to interact with this process status file in the memory. So even though you can say that this process reads two different files, and in a typical scenario, they cannot be interacted, but in the memory, they can be interacted. So to do not miss any system entity interactions, we will also include these interactions for security analysis.
Okay, cool.
Yeah, I think it's very keen observation. So it's very similar to the may analysis and the must analysis. So may means that these two causalities may happens, and must is basically saying that these two causalities must happens. So I think based on different heuristics, you will construct different graph and it leads to different findings, right? It's more like a user configurable settings.
Yes, correct.
All right, so great, good questions. Any other questions here? If there's no other questions, let's move on.
Yeah, sure, thanks. So yeah, if you have any question, just feel free to interrupt me. Okay, so while system entities, site information plays an important role in determining their semantics. Such information is not encoded in a provenance graph or bipartite graph. However, a recent study have shown that site information of system entities can be inferred from the context in which they are used. As a result, to incorporate a high-order connectivity as the recommendations, we aim to combine system entity contexts that represent the site information and the system entity interactions into a knowledge graph. And in this work, we define a knowledge graph as a set of triples. Each triple has three elements: head, relation, and tail. Head and relation here denote the system entities, for example, of the password file. And the relation denotes a system call or a system entity interaction. So taking the a notch graph as an input, our key idea is to use the different order connectivities or multi-hop passes in the graph to model the likelihood of system entity interactions. Towards this end, we first model first order connectivity to parameterize system entities as embeddings or vectors. Then we model higher order connectivity by propagating embeddings from neighbors in the graph via graph neural networks. And at last, we classify system entity interactions into normal and anomalous.
So the final is looking to the whether the interaction is abnormal, not an entity.
Yes. So here are the system entity interactions form the basis for cyber threat analysis in this work. If we find that,
when you try, sorry, so maybe I raised a question too early. So once we find an interaction is abnormal, so basically we're looking to the path, right? So it may go through several hops from node A to node B. So you reported that path as the recommendation.
Yes, correct.
Kushal, we have another question. Here,
yes, you were mentioning higher order connectivity, and we know that GNN corresponds to, I guess, the first Weiss-Feiler lemon test, and we remember that it was weak because it doesn't capture the higher order connectivity, right? It doesn't capture like third or fourth order connectivity. So aren't you limited by GNNs here, or am I mistaken?
Yeah, so here the number of orders we try to capture is determined by the number of information propagations in the graph neural networks. Of course, if you only set the number of propagations in the graph neural networks, for example, as three, then we only consider we only consider the three hop passes in the high order connectivity information. Of course, it's a limitation. Yeah.
Yeah. Okay.
Yeah.
Sorry. So you're saying you were saying that interaction is not a hop limit.
Oh yes, the interaction is not. But here, when we propagate the information from neighbors, we do set up the number of propagations.
That's where you train the GNN.
Yes.
Okay. Oh, by the way, so when you train the GNN, so you're looking to both the black and the blue edges. Am I right? Or you're just looking to the black one?
Yeah, the black one are system calls. We basically use them to do the first order embedding. So we use this black ones to decide or to just convert the system entities into vectors while preserving their semantics. And here we use
so the answer is that you do not using the blue edges for the embedding propagation.
Yes, but we do use that to do the information propagation.
Oh, sorry. So what's your difference between the embedding propagation and information propagation? So the embedding propagation is for training the neural network model, and
yes,
and how this information propagation used to train the model, or it doesn't matter.
Oh, so as you can see in a notch graph, we have different types of edges, right? The system calls, different system calls and connections, and we will unify them as relations. Yeah, not blue. The relations here. So this is a notch graph, and in the notch graph we have edges, right? And these edges will be used to propagate the information. And these edges can be interactions and the system calls. The black ones represent the system calls, and the blue ones represent the interactions, right? So while I forget the name. So previously a student said that the approach will be limited through the number of layers for information propagation in graph neural networks. And we try to mitigate this limitation by also propagating the information through interactions. So for example, for this one, for this node and this node, so we can say that they are far from each other in the graph, but we can still propagate the information between them. And that is because we consider the information propagation based on interactions.
Okay, so the basic idea is that it's a blue interactions is basically a mitigations for the multi-hop propagation on the black edges. Okay.
Yes, it will be used to capture high order connectivity.
Okay, yeah, I think that's quite clear. And maybe I keep my questions maybe to the few later slides. And the students will have the questions for Zeng. Okay, if not, let's keep move on.
Yeah, okay, thanks. Okay, so here by modeling first hop connections in a graph neural network, we aim to map system entities into a vector space while preserving their semantics for similarity analysis. And our intuition is to use the system context to decide the semantics of system entities. To do so, we use a knowledge graph embedding method, TransR, which uses head plus relation in a knowledge graph table to define the tails, which mirrors our intuitive understanding of using system contexts to define system semantics. And it's worth mentioning that TransR will assign distinct semantics to the same system entities, conditioned on different relations. For example, here, if the GT cache process is used on the write and unlink relation context, it will be given two different embeddings, which indicates different semantics.
And how do you embed the entity by themselves? So for different nodes, do they have different features? And how do you let alone the context? And how do you unify the embeddings of different types of nodes in a graph?
Okay, so basically we will first use one-hot encoding to encode the system entities here, and then
one-hot.
Yeah, one-hot.
So what if the process, as long as process name is different, you're just using different vectors to do this, and so basically you construct a dictionary.
Yes. So basically, we will have the embedding table or embedding dictionary to represent the embeddings for individual system entities. And then we will use this learning algorithm to optimize the embeddings for system entities and while preserving their semantics.
And do you pre-train a model? So it's more like a word embedding, right? So you have a dictionary and convert it into a more intuitive embeddings. So what pre-train, do you have some pre-train task for that?
Yes, that's a good observation. So basically this TransR is used as a virtual VAC in our approach. But the thing is that we do not do the pre-train modeling. We will also include the loss function of this TransR into the final objective function. So you can consider that this algorithm is used to capture first order connectivity, the first order connectivity information. And later we will incorporate the high order information and then combine them for the final recommendation or for the final objective function.
Yeah, I understand. You have maybe you were designer, you have an objective, you learn everything there, but I'm not sure, maybe you can design some pre-trained task so that you have a good starting point. Maybe, I don't know.
Yeah, that's quite popular nowadays. You do the pre-training model. Maybe you can even achieve the better results, or you can reduce the training overhead.
Yeah, so maybe you mask some nodes and let them predict its neighbors, or you predicting some system calls between two nodes, whatever. So as long as there's embeddings can achieve that subtask, maybe you have a better starting point.
Yeah, that's a good idea.
Okay.
representation learning, yeah, for the system entities.
Yeah.
Okay. Okay. So beyond the one-hop connections in a knowledge graph, multi-hop passes are inherent in the graph. And such high-order connectivity not only supplement the similarities among system entities, but also exhibit how system entities influence each other. For example, the left two-hop pass shows a similarity between two process status files because they both interact with the GT cache process. And the right three-hop pass describes how the password file is transmitted out of an enterprise. And to capture
when we do the embeddings, whether the types of the nodes will be considered.
The types of
the
nodes.
The process. So given embeddings, is there a specific dimension to indicating in this process? It is files, it is servers.
Oh yeah, in this SHADEWATCHER, we do not differentiate whether a system entity is a process or a file or a network socket. But after we use TSNE to visualize the embedding space, we will find that the process will be clustered together and far away from the files.
Even if you do not specify the type.
Yes, correct. And that is because we use trans-R to embed them, and in trans-R, the relation matters. The relation plays an important role to in deciding the semantics of system entities. And for example, the files will never be used in the context of fork or SQ, right? And the process will also, it will never be used in read system calls. I mean, you cannot read a process, right? Or you cannot fork a file. Yeah.
I see.
Yeah. So here, to model the high order connectivity, we adopt a graph neural network to iteratively propagate embeddings along with multi-hop passes in a knowledge graph. And we also design a number of optimizations in the graph neural network. For example, we will differentiate the different importance of neighbors while we aggregating the information from neighbors. And then afterward, we will aggregate the embeddings from all the propagation iterations to form the final embeddings of system entities. And by doing so, we can capture different order connectivities in the system entity embeddings. Okay, so after obtaining the system entity embeddings, we will apply inner product on them to predict how likely a system entity would not interact with another system entity. And such if the likelihood is beyond our predefined threshold, then we would classify this interaction as a potential cyber threat.
Sorry, I think I missed something here. So the detection is giving T is an interrupt, H is a nodes, and the T is another nodes.
Yes.
And what's your training objective?
Okay. So good question. So basically here we will consider all the. So first of all, we will train our model on the benign dataset. And we will consider all the interactions we can observe in the benign dataset as negative samples. And then we will simulate the interactions not observed in the knowledge graph as positive samples, and use these positive and negative samples as supervision signals to train our model.
So basically, you're sampling the constraint knowledge graph, and if there's a hops interactions, it is normal, and if we don't see any interaction, it is abnormal. So basically, it's transform it into a classification problem.
Yes, correct. And as you can see here, it's quite tricky because the interactions we haven't witnessed, we previously do not see, are not exactly malicious interactions. However, this sampling, this negative sampling or positive sampling is often used in recommendation scenarios because it's reasonable to rank the system entity interactions existing in the knowledge graph lower than that do not exist in the knowledge graph. So it's basically, you can consider this idea of training as a anomaly detection scheme.
Yeah, I understand. Okay, so that's why you're just using dot product. So because the dot product is just one of the objective function. It's basically the pure objective function. Is there anything else? It's just a dot product as a final objective.
Yeah, it's a final objective.
Okay.
Okay.
Mm.
Okay, so here we to keep up with involving system entity interactions. We also enable dynamic updates of our recommendation model with analyst feedback on detection signals. And the details of these dynamic updates can be found in our paper.
Yeah, I still a bit sorry. I just, so you want to skip this, how you're going to go to the manual feedback to evolve the model, right? So you're talking about analyst feedback is that when you recommend something the human cannot prove, and they want to provide feedback to update the models or something else.
It's like, for example, if you, as we all know, the system behaviors will change over time, right? And in that case, SHADEWATCHER may raise false alerts for benign system activities. So in that case, so for example, in a security operating centers, the security analyst will continuously shift through the alerts and find the false positive ones. And here we will use these false positive ones to retrain our model to keep our model adapted to the involving system interactions.
Okay, so maybe I have one more questions here. So comparing to the original training point, you're more like a augmentation, data augmentation, right? So sometimes it is false positive, sometimes false negative, and the people and the analyst just pick up some telling the systems if you're wrong. So in this case, the number of manual annotated samples is much smaller. The number of that is much smaller than your knowledge graph sampling. And how do you manage the imbalance problem? If you keep training the feedback data, maybe the model have some forgetting effect on the old data. But if you merge them all together, and that number could be too small to be inferential.
Yes. So here, first of all, I need to claim that this is not our main contribution, and this is basically like an open research question.
Yeah. And so it just makes the approach more complete. Yeah, that's it. Yes. Once you have this component, if as a reviewer, it feels good. It feels good. Yeah.
Yeah. So basically, we do not consider the imbalanced data here. So what we do is to simply involve this new data to the old data and retrain the model. And we find that the false positives can be reduced. Yeah.
Okay.
Yeah, thanks. So to evaluate the SHADEWATCHER, we use 6 real-world cyber attacks simulated in a testbed environment and 4 APT attacks from the public DARPA TC dataset. And we focus on the following aspects in our evaluation. First, how effective is SHADEWATCHER as a cyber threat detection system? To what extent do different order information facilitate cyber threat analysis? And how efficient is SHADEWATCHER in deployment? In terms of SHADEWATCHER's effectiveness, we aim to identify cyber threats based on system entity interactions in the DARPA TC dataset and our simulated dataset. The DARPA TC dataset consists of over 68,000 malicious interactions and about 8 million benign interactions. Our experimental result shows that SHADEWATCHER misses 10 malicious interactions, and its overall false positive rate is well below 1%. The simulated dataset consists of 39 malicious interactions, and 2 of which are missed by SHADEWATCHER. From this table, we can observe that SHADEWATCHER distinguishes benign and malicious interactions in audio records with a high accuracy.
Sorry, so for this experiment, so these 68K malicious are the labeled malicious events, or it is a more like a simulated, you inject these malicious data into it?
Oh, they are labeled, they are manually labeled following the public attack documentation.
Okay, so in this case, in terms of the malicious event detections, you almost, there's no room for people to improve you, right?
Not really, because the false quality rate is still very high, and we are challenged in the paper reviews. So, for example, if you consider that there are over 1 million system interactions, which is quite normal in modern systems, and in that case, our system will generate numerous.
So, which means, given the data, your true positive, so you can see the false positive rate. So which means your precision is close to 99.6.
Yeah,
right.
But the thing is that I noticed that one of recent work, the Unicorn published at NDSS 2020, they can achieve almost 0 false positive rate.
Okay.
Yeah, in this DARPA TC dataset. But their problem is that they produce the detection signals at the coarse grain level, at the behavior level, and it requires tedious manual efforts to review the records in the behavior. And here we focus on the interactions, which is a much finer. Yes.
I got it. Okay, so and so questions for this data set, and when was it published?
Oh, here the public TC dataset is released in 2018, and for the simulated dataset, we aim to reproduce the cyber attacks from related works published within 5 years. Yeah.
And here, so will you please go back to the previous slide? And
yeah.
in terms of the attacks, right? You have 10 attacks and 6 cyber attacks and 4 APT attacks.
Yes, correct.
And these attacks, and so the first 6 are you just injected the attacks in the test bed.
Yes.
And you're basically, so your next slide is basically talking about the 4 APT attacks.
So
and
here
both.
Yes.
So the first data set involves 4 APT attacks, and the simulated data set included the 6 simulated cyber attacks.
Yes, correct.
And it seems that since the simulated attacks are simulated by you, why not increase its number? So giving the scalability of the simulated data, it involves only maybe less than 100. And why not to improve the simulation trials?
You mean get more?
Yeah, getting more. Yeah.
So okay. So of course, it will strengthen our paper if we can get more cyber attacks. But in this field, 6 real-world cyber attacks are enough in the
what I mean is that for this configuration leak up, so you can just keep injecting it in different scenarios, in different systems, and you consider all those as one malicious event or multiple malicious event.
The multiple. So for each attack here, we will perform the attacks and collect the associated system logs. And based on the system logs, we will label the malicious interactions.
Yes.
So for example, each attack will consist of not only one malicious interactions, but multiple malicious interactions.
I see. So what you recorded is a number of malicious interaction.
Yes, correct.
And my question is that, so for example, given a configuration leakage, and we keep on injected a simulated attack. So maybe for 1 week or 1 month, and for every days we attack it for several times. So this will be quite a number. That will be quite a number. So is that does it make no difference we attack for multiple times, or we attack once, that's okay, that just be okay. So it seems that it's 6 attacks, and each attacks involves several interactions. So you just injected the attack once, and you just record it, you just see whether you can detect it, and that's all.
Oh yeah, I got your question. So here, even though, for example, even though you can perform the configuration leakage multiple times, for example, in a week, but since the behaviors or interactions are similar, we assume that the SHADEWATCHER can also distinguish the benign and the malicious interactions. So here, the key point is to analyze the semantics of the system entity interactions. So as long as the semantics remains the same, we can still detect it. So we do not need to, for example, perform these attacks many times in a long period. Yeah.
Okay, that clarifies. Thanks.
Okay, thanks. Okay, so to answer how different order information in the knowledge graph facilitate attack investigation or cyber threat analysis, we compare different knowledge graph embedding algorithms and study the importance of high order information propagated by our graph neural network. And the results are summarized in this table. The combination of TransR and the graph neural network represent our SHADEWATCHER. And compared with one-hot encoding, TransE and TransH, TransR's advantage is to distinguish the semantics of system entities conditioned on different relations. From this table, we see that SHADEWATCHER achieves the best performance in terms of the AUC values, and which implies that high order information is beneficial for cyber threat analysis, and it's important to distinguish semantics under different relation contexts. Okay, so the final part is about the system performance. We measure the runtime overhead on the DARPA-TC dataset at different phases, and all experiments are performed 5 times, and we report the main result in this table. We observe that SHADEWATCHER can pinpoint cyber threat from nearly 1 million system entity interactions within seconds. And we notice that we get this number by running SHADEWATCHER on high-performance GPU machines. And after performing further experiments on CPU machines, we find that SHADEWATCHER can still finish the interaction classification within 4 minutes, which is still practical in real-world scenarios.
So sorry, the feedback. So which part is the feedback part?
So we do not include the feedback in this part.
Okay, no problem.
Okay, so here, to gain further insights, we use an APT attack from the DARPA-TC dataset to demonstrate how SHADEWATCHER uses the recommendations to guide cyber threat analysis. So simply speaking, in this attack, attacker's goal is to exfiltrate the password file. So in the cyber threat analysis, SHADEWATCHER will first extract all the system entity interactions, and then gives a recommendation score for individual interactions. As we can see here, the interaction between the password file and the network socket is given a high probability of being malicious because it represents data exfiltration activity. On the contrary, the interaction between the GD cache and the process status file is given a low probability of being malicious because it represents perfectly normal process status retrieval activity. So
Okay,
Yeah.
please,
Any
please,
question?
please, you can finish on have a conclusions, and we have some maybe 2 questions follows.
Yeah, no problem. So nowadays, cyber threats are everywhere, leaving traces of shades in the victim systems. And to review shades, we propose the SHADEWATCHER to analyze cyber threats through recommendations on system entity interactions. It models a system entity's preferences on its interactive entities. Our key insights are that similar system entities would share preferences on their interactive entities, and high-order information can better correlate similar system entities, even though they are disconnected in a progress graph. Yeah, thank you for your time and
all right,
attention.
so there's a very fancy logo, right? Sensing the movement, the sun and moon from their shades. Okay, that's why you can say the SHADEWATCH.
Yeah,
right?
that's
So
how we come up with the name.
Just like a light and to let all the shadow
to be revealed.
Yeah. Okay, that sounds a very nice tool's name. Okay, so maybe I have one question for your adversary. So have you ever considered your adversary? So assume the attacker has known your defense, and what's he gonna do to evade the detection? So it's more like a SHADEWATCHER, right? So what if they want to do this?
Yeah, that's a good question. So nowadays we can see a lot of adversarial machine learning approaches, right? They can, for example, their goal is to invade the detection, and our SHADEWATCHER is also limited or suffer from this type of attacks. For example, attackers can add or delete edges in the notch graph to misguide the
how could they do that? So which means that you have a different behavior.
Yes. So for example, like social network, in a social network, you can just add the edges or delete the edges between 2 people. And here, just say, in the notch graph, you can add or delete edges between 2 system entities. For example, we can add noisy or irrelevant system entities or system entity interactions while performing the attacks or in parallel to the cyber attacks, and that may influence the final recommendations generated by SHADEWATCHER. But in the paper we say that they might be a potential future work, because even though you can add or delete edges while in the notch graph while performing different attack behaviors, but it's very hard to do so because, first of all, you cannot just arbitrarily add edges between 2 system entities. For example, you cannot use a file to read another file. You can only use a process to read a file, right? And also, you cannot just delete any edges you want. For example, if your goal is to exfiltrate the password file, then there must be an interaction between this password file and the network socket. So a research question is how to invade this type of attacks while still achieve the malicious goals.
Yeah, so I'm thinking about an adversary. So I'm not sure what is the real adversary. So you have embedding, right? You have embedding of different process, different file names. So what if attacker just change a very strange name? So for example, I'm going to hide my name into some benign names, like for example, I'm using these the main name, right? So whatever, so the benign name. I cannot name one, but you can name it. So what I've changed my name into a benign process name, or if I change it into a name which is outside of the vocabulary or dictionary, and can the system work?
Oh, yes, it will work. So the beauty of our of this SHADEWATCHER is that we do not decide the semantics of system entities.
What I mean no, but the name basically is a dictionary, right? So suppose you start with one hot, so which means that this process name will have exactly the same embeddings of some benign node. I understand that when you're embedding the context information, that it will have different embeddings. But what if the process name is outside of dictionary? So which means that you cannot find a one-hot version corresponding to it. And how do you address this from a technical point of view?
Yeah, good point. So here we do not just use a name to identify system entities. For example, process name. We use a combination of processes ID and its parent ID and also its name to represent or to identify a process.
But the process ID can always change, right?
Yes, and the process ID can also be cycled in a system while you restart a system. So here we aim to use a combination of process ID and the process name to identify processes.
Yeah, so which means that if I write a malwares and suppose it were hiding to, so basically process ID does not have any strong information to identify it itself. So which means that suppose there's process of fires and it have a different name and different process name, and it's embedding somehow out of the one hot dictionary, right? And how do you embed this kind of the process name?
Yeah, so in that case, we can only infer their meanings by how they interact with the systems.
So you will have so all the unknown process name and file names will be shared one embeddings or one initial embeddings.
No, they will have their own embeddings and
based on the process ID.
Yeah, based on the process ID and the process name. So basically, they will be initialized with a random embedding, and then
random embedding.
Random.
And you will guarantee that these random embeddings will not be in the one hot, but you started with one hot, right? So you cannot have random.
Yeah. So basically, you can say it's a dictionary, right? Or it's an embedding table. So as long as we encounter a new system entity, we will add this new system entity into this table and initialize the embedding for it, and it's a random.
So if it is you add one more word, so the length of the embeddings change when hot embedding change. So and which means that the what2 vector, you need to retrain it, or?
Yes, we need to retrain it. That's why we claim that our approach now currently is designed in an offline setting, because for an online setting, we will always encounter new system entities. And in that case, we have to retrain the embedding table to update the semantics of individual system entities.
Yeah, maybe we need to generalize this part in the future. I think in terms of productions and the new, I think for the attacker, it's very easy to change a new process name and file name. That's supposed to be common. And also the new malware is emergence every day. Yeah.
Yes, correct. So yeah, so we can, so currently what we can do is to infer their semantics by their context, not by their names.
Yeah, and also another comment is that have you distinguished the type of process which may mitigate the problems of the process name information? For example, suppose the fire, if you can check the fire, I'm not, because after the system log, you do not have more details because maybe this malware has gone, maybe the fire has been deleted. But if possible, we can further categorize, just giving your examples of collaborative recommendation, right? So the Alice and Bob likes a movie, and this movie belongs to the actions and maybe science fictions. And is that possible to build a mentor knowledge graph behind? So which can help you to generalize the technique better.
Yeah, that's a good idea. So yeah, of course. So as you can see in this project, we still look into the system entity interactions. We do not look the real citing information behind the system entities. Of course, if we can instruct the citing information to represent the system entities, we can get the higher quality representations for the system entities. Yeah, that's a very good point.
And yeah, so maybe so basically when you extract data, in terms of extractions, using the state-of-the-art approach or the off-the-shelf approach, right? So maybe I'm not sure because I'm still an outsider yet. Maybe when you extract the more information from the log, you can just dive into more details of what a message it is, or what exceptions reported of certain events. Maybe that can also help.
Yes, correct. And you can also differentiate the importance of this setting information for the final representation learning.
Yeah, I think I have finished my questions. Sorry for keep interrupting you, but I think it's really good opportunity. So Zeng is first author of this Auckland paper. We know how hard and how challenging we get one paper accepted in Auckland. And it is really a good and congratulations again. And it is really a good opportunity to find the first authors and present all the details. Usually the information lies beyond the papers. So when we organize paper presentations and the future students were giving the presentations, and when there's some detailed information, sometimes details matters, we have to guess, we have to criticize unintentionally. But this time when Zeng is here, so I think it's really a good opportunity to raise your questions, to interact it, or maybe you can have offline discussions. So besides me, is there any other questions for Zeng?
Well, I wanted to ask one thing. Have you experimented that dynamic update thing? Does it take too much time, or does it even helpful?
You mean the dynamic updates?
Yes, the processes change. They continue to interact, so we need to update the graph, or sometimes.
Yeah. So in this presentation, we do not introduce the details about this part of evaluation, but in our paper, we do evaluate how these dynamic updates will facilitate the cyber threat analysis, and we find that it's helpful. If we can include the more information, we can include the NS feedback on detection signals. We can indeed reduce the false positives while performing the cyber threat analysis.
Oh, cool. Yeah, thanks for the awesome presentation.
Yeah, but yeah, thanks for mentioning this point. And the thing is that we do receive a lot of pushbacks about these dynamic updates, and that's why we do not include. We decided to not include that in our presentation because it basically include the attack service, right? A new attack service where the adversaries can use it to poison our recommendation model and misguide the cyber threat analysis. Yeah, we do receive a lot of pushbacks from the reviews.
So it seems along. Yeah. So it sounds like the reviewer, you have a hard time with the reviewer.
Yes.
Yeah, I think that's not easy. So we once have some unique security papers, and the reviewer really picky. So sometimes 5, 6 reviewers, and they even run our experiment data and giving some feedback. But it's quite a anyway. So the challenge work is quite rewarding.
Yeah, that's true.
All right. So any questions? If there's no questions, let's thank our speakers again. So that's really excellent presentations and very novel and interesting work. And maybe there's a lot of work for us to learn. Yeah.
Okay.
Okay. Yes. Thanks, Zeng. Maybe that's the end of talk. Thank you very much.
Yeah. Okay.
Okay. Bye, everyone.